On this video, we will talk about the tangent line of a circle. So let's start by looking at the following figure. It states the following figure shows a circle and a line that is tangent to a circle. So how would we describe a tangent line? Well, let's identify it. So this is the circle that is given to us. So here we have our circle. And now this is the line that we are claiming to be a tangent line. Now, how will we describe a tangent line? Well, let's see how this line is interacting with the circle. Well, it seems like this tangent line, it's only touching the circle at one point and one point only. And that's actually how we're going to be defining tangent lines. So a tangent line, it's a line that intersects a curve, which in this case, right now, our curve is a circle. It doesn't always have to be a circle. It's just a curve, so any kind of a silhouette. So a tangent line, it's a line that intersects a curve at one point only. And this is pretty much the definition of a tangent line. A tangent line is just a straight line. It has to be a straight line. It cannot be a curvature line. So it is a straight line that intersects a curve, which in this case it is a circle, and it only intersects at one point and one point only. So this will not be an example of a tangent line. Let's say we have a circle, and now we have a line that intersects this curve at two different points. So this is not an example of a tangent line. It only has to be intersecting the curve at one point and one point only. But in this lesson, we're going to concentrate on circles more than anything. So let's start discussing some properties that this tangent line has with circles. So let's take a look at this following task. So for this task, I'm actually going to open a compass. So here it says, given the following circle, let's construct a line that is perpendicular to the given radius and passes through point P. So let's see. So here we have the circle. Let's start by extending this line, which is we're just going to extend the line of the radius, because what we want to do is we want to create a line that is perpendicular to the radius. And let's see the relationship that it has with the circle. So recall that in order for us to create a perpendicular line, we got to create our circle of rotation. So let me just get in here. Let's create our circle. Let me draw a new color for us. So let's make it blue. So here we're going to make our mark. Let's rotate. We're going to create another mark. And now we're going to go to our mark, open our compass, more than half. Yep, that's enough. More than half. And then we're going to create our mark over here. And we're going to do the same for the one at the bottom. And use the same length. We're going to use it on the second mark. So here we have our mark. And here we have another mark. Oops, let me just go back to it. And if we remember that if we connect these two intersections, that's how we're going to be creating our perpendicular line. So let's just create these 2 points. So here we have our intersection now. And now let's just zoom in. Let's try to zoom in a little bit. And note that after zooming in, notice that this perpendicular line, which is represented in purple, this purple line, it's definitely perpendicular to the radius. And now, besides just being perpendicular to the radius, what other interaction does it have with the circle? Well, it seems like it's only touching our circle at one point and one point only. So what observations do we have when it comes to tangent line? Because now notice that if this perpendicular line is touching the circle at one point, then we can call this a tangent line. So now the question becomes, what relationship does a tangent line have with the circle? Well, it appears that the tangent line is perpendicular to the radius of the circle at the point of intersection. Notice that the tangent line is definitely perpendicular to the radius of the circle, and it is perpendicular at the point of intersection. So that's what we can choose right here. So here we have our relationship. The relationship is that the tangent line is perpendicular to the radius of the circle. And where is it perpendicular? So it is perpendicular at the point of intersection. So here we have our first property for tangent lines in circles. The tangent line will always be perpendicular to the radius of the circle at the point of intersection. So now let's take a look at this following task, which is going to demonstrate another property of perpendicular lines. Well, it says the following figure shows two tangent lines, PA and PB. So here we have that PA and PB are tangent, so therefore it only touches the circle at one point. But now what else do we know? Well, if PA and PB are tangent lines, so therefore let's assume that this is the center of my circle. So therefore, if I were to just connected the radius of the circle, based on what we just discovered previously, I know that that will be 90 degrees. The intersection, it will be of 90 degrees. We just showed that a tangent line is perpendicular to the radius. And the same can be said about the bottom here. The same can be said about the bottom here. So given this information now, do you think there's any relationship between PA and PB? Do you think there's any relationship among line segment PA and PB, which is a line segment that is coming from tangent lines? Well, let's see. I mean, they kind of seem to be congruent, but how can we make sure, how can we show that they're actually congruent? Well, how about we draw an auxiliary line? Let's draw an auxiliary line from point P all the way to the center. So now that we have this, notice that we have created two right triangles. We have our right triangle. Let me actually give it a name here. Let me call this point O. So we have a triangle, POB, which is a right triangle because we do have 90 degrees on it here. And we also have PAO. Well, is there any relationship among those two? Well, notice that AO and OB are the radius of the circle. So therefore, these two line segments must be congruent to each other. In addition, also notice that PO is congruent to itself. So now notice that we have two triangles where two sides and an angle are congruent. But most importantly, notice what kind of a triangle it is. It is a right triangle. So therefore, by the hypotenuse leg theorem, if I know that AO is congruent to BO and PO is congruent to PO, then by the hypotenuse leg theorem, because notice that these two right triangles, they both have the hypotenuse congruent and they both have one angle, one leg that is congruent, then therefore, by the hypotenuse leg theorem, POB, well, not just POB, but triangle POB is congruent to triangle POA. And therefore, PA must be congruent to PB. So what is this trying to tell us about tangent lines? Well, what this example was trying to show is that given two tangent lines that are coming from the same point, let me actually erase this so it might be a little bit confusing with our explanation now. Given two tangent lines, which in this case it's PA, and in this case that's PB, given two tangent lines, and if those two tangent lines intersect at a point, which in this case, notice that PB and PA, they intersect at point P. Whenever you do have this situation, then therefore those line segments will always be congruent. So if two tangent lines are on the same circle and they intersect at a point, then the line segment from the point of intersection to the point of tangency is going to be congruent to the same point of intersection to the other point of tangency. And this is very important when it comes to circles and tangent lines. So now let's just fill in the blank. It says if a line in the plane of a circle is perpendicular to a radius and its outer point, then what kind of a line should we be having? Well, based on what we discussed in task number 1, which we did have it over here, we can make the claim that if we have a tangent line, then it's perpendicular to the radius. So therefore, if you have a line that is perpendicular to the radius, then it must be a tangent line. Then the line is tangent to the circle. So now we have a couple more illustrations that I would like to discuss with you. So looking at example 4, this is more like kind of vocabulary introduction. It says, in the following figure, we have a line segment AB. And AB is said to be common internal tangent. It's a common internal tangent line. So we're saying that this line segment, AB, well, it's not even a line segment, but it's just a straight line. We're saying that this tangent line, or this line, that notice, it is tangent at two different points. And each point corresponds to an individual circle. We're saying that this line is called a common internal tangent. Now the question is, how will we define or describe a common internal tangent line? But notice that the first thing that we can notice is that this line, in order for it to be a common tangent line, then this line is tangent to two circles. So the first thing that we know is that this line must be tangent to two circles. But what else? Well, also notice that it intersects the segment joining the centers. Because notice that here we have our first center and here we have a second center. If I connect the center of those points, notice that this tangent line, it's also intersecting the line that connects the center of the circles, which this line is tangent to. So a common internal tangent line has two characteristics. It is tangent to two circles, and in addition to that, it also intersects. It intersects the segments joining a center. So now we have another kind of tangent line, but now notice that this is called the common external tangent line. Well, it is a common tangent line because notice that here RS, it does have the property of a common tangent line because it is a line that is tangent to two different circles. So how would we define a common external line? Well, the first thing, if it's a common tangent line, then therefore it must be tangent to two circles. But what else? Well, notice that now, if we connect or we create a line that intersects the circle or the center of two different circles, now notice that this what so-called common external tangent line, it does not intersect the line that is connecting both centers. So it does not. Intersect the segment joining its center. So in order for them to be called common tangent line, it must be a line that intersects at two different circles, and it must have a tangency point. But in order for it to be called a common internal tangent line, it must also intersect the line that is joining the center of those two circles. And in order for it to be called a common external line, it still has to be a common tangent line. So there's a line that is tangent at two circles, but now it is external. It does not intersect the line segment joining both circles. So here I have one more idea to discuss. So it says a circle can be tangent to a line, but it can also be tangent to another circle. The following two figures show a pair of tangent circles. Take a look at the following figures and let's give a definition for tangent circles, give a definition for externally tangent circles, and give a definition for internally tangent circles. So note that these both figures, they both represent what we call tangent circles. Now, looking at figure A, let's call this figure A, and let's call this figure B. Looking at figure A, notice that here we have a circle, and here we have a bigger circle, and they seem to be tangent to the same line. But most importantly, they're tangent at the same location. And notice that we also have the same scenario here. We have a small circle, and we have a bigger circle, and they seem to be tangent to line K. But most importantly, they seem to be tangent at the same location here. So this is actually how we're going to be defining tangent circles. So tangent circles are just circles that are tangent to the same line at the same point. So if we have two circles and they are tangent to the same line at the same point, we call those circles tangent circles. Now, an external tangent circle, that's an example, or that's the illustration for A. Externally tangent circles are circles that are tangent to the same line and at the same point, so they're tangent circles. That are next to each other. Such as an example A. Notice that in A, we have two circles. They're tangent to the same line at the same point, and they're not overlapping. They're actually one next to each other. And internally tangent circles are tangent circles where one circle is inside the other. Just like in example B. Here we have two tangent circles. I know that they're tangent because they're tangent to the same line at the same point. And more importantly, the smaller circle is inside the bigger circle, not like we had it in example A. And with this concludes our lesson for tangent lines and circles.